In this video, we're going to continue to look at experimental techniques. We're going to look at different methods for collecting and drying of gases. Now in chemistry, there are many reactions that will produce gases, and before we can identify them, very often we will need to collect the gas first. Okay, one method for collecting gases we have already learned in the previous video is to use a gas syringe. Okay, so for example, we have a conical flask, and then this reaction is producing some gas. So how do we collect the gas is to connect the reaction flask with a gas syringe. Okay, the connector is known as a delivery tube. So in this case, the gas will be collected in the gas syringe. This is one method of collection. Okay, in the next slide, we're going to look at three other methods. The three other methods are displacement of water, downward delivery, and upward delivery. So on the right of the slide, I've included the experimental setup for the three methods. I hope from the names of the methods, you'll be able to match the method to the experimental setup. Okay, so I hope that you can see that displacement of water is actually your setup C. So what happens is that when the gas enters the delivery tube, it will displace the water in the glass jar. Alright, so your gas will be collected over here. In some textbooks, they call it the downward displacement of water. Okay, next, downward delivery corresponds to setup A. Why do we call it downward delivery? Because the gas is being delivered downwards into the into the gas jar. Okay, and then upward delivery corresponds to setup B, where the gas is delivered upwards into the gas jar. So now that we have seen what methods are there to collect gases, now we need to know which method to use for a particular gas. Alright, for the displacement of water, there must be one property associated with the gas, okay, before we can use displacement of water. And for us to tease out the property, we need to imagine the journey of the gas. Alright, so the gas passes through the delivery tube, and it goes into water. It goes into water first before it displaces the water in the gas jar. Alright, so in order for the gas to be collected using this method, it cannot, be soluble in water. Okay, so displacement of water is only suitable for gases that are insoluble in water. What happens if the gas can dissolve in water? Then cannot, because what happens is that when the gas passes through water, it dissolves in it, it is not collected. So for gases that are soluble in water, we can only use downward delivery or upward delivery. Now, which one to use? For downward delivery, the gas actually is being delivered downwards. So it is used for gases that are denser than air. Okay, so it actually sinks. So once it's collected over here, since it's denser than air, it will remain in the container. It will remain in the gas jar for a long period of time. Upward delivery, the gas is being delivered upwards. So it's used for gases that are less dense than air. Okay, so because it's less dense than air, it floats, so it remains in the container for an extended period of time. Okay, so for this slide, we need to learn this. Displacement of water is for insoluble gases. For soluble gases, we need to use downward delivery if it's denser than air, or upward delivery if it's less dense than air. So the natural question that comes next is, how do I know whether a gas is soluble in water or insoluble in water? How do I know whether a gas is denser or less dense than air? So there's a very simple answer to that. And the answer is that you have to memorize them. you have to memorize the properties stated in this table. Okay, there are, I know it looks intimidating, there are 7 gases. For solubility, there's nothing much that I can help you. You have to memorize. For density, I'm going to teach you a hack later. So you don't have to memorize. By applying the hack, you will be able to know whether a gas is denser or less dense than air. So to apply what we have learned in the last slide, displacement of water can only be used for the first 3 gases. Okay, in fact, it's not ideal. It's not ideal for carbon dioxide because carbon dioxide is already slightly soluble. Alright, however, it can be proposed for the first 3 gases. It is optimal for the collection of hydrogen and oxygen. Okay, it's also important for you to remember that oxygen is very slightly soluble as compared to hydrogen, which is insoluble. Okay, this concept is actually being tested in a later chapter called electrolysis. Next, the 4 bottom gases cannot be collected using displacement of water. Why? Because they will dissolve in water. So we can either collect them using downward or upward delivery. From the density, you can see that the first 3 of the lot, we need to use downward delivery, and then the last one, ammonia, we have to use upward delivery. So now I'm going to teach you the hack for you to know whether a gas is denser or less dense than air. And for that, I need to refer you to the periodic table. If you look at the periodic table, for any particular element, there are 2 numbers associated with it. Now the smaller of the larger of the 2 numbers is actually your relative atomic mass. Okay, it's essentially in a very crude way the mass of an atom. So in order to know whether a gas is denser or less dense than air, we first need to know the formula of the gas. For example, carbon dioxide, okay, it has a formula of CO2. Okay, hydrogen, it has a formula of H2, and then oxygen has a formula of O2. Once we know the formula of a gas, we can actually calculate the relative mass of the gas. Okay, how do we do that? Is to sum up the atomic masses of all the atoms in the formula. For example, carbon dioxide has 1 carbon and 2 oxygens. Okay, so if you were to find the atomic mass for carbon, it's actually 12, and the atomic mass of oxygen is 16. There are 2 oxygen atoms, so 16 times 2. So the molecular mass, the mass of carbon dioxide is actually 44. Okay, doing the same for hydrogen, you'll find that the mass, the relative mass of hydrogen is actually 2, and the mass of oxygen is actually 16 times 2, which is equals to 32. Alright, so from here, how do we know whether it's denser or less dense than air? We compare the mass, the relative mass of the gases with the mass of air. Okay, the mass of air is roughly 29. So if the mass of the gas is greater than 29, then the gas is denser than air. If the mass is less than 29, then the gas is less dense than air. Okay, so there's no need for you to memorize whether a gas is denser or less dense than air. What you can do is to compute the molecular mass, alright, by summing up all the atomic masses and then comparing it to the mass of air, which is 29. Now earlier I mentioned that in chemistry many reactions produces gases, and very often we need to collect them in order to analyze and identify them. But there's actually a step that's very essential prior to collection in order for us to make a correct analysis. Why? Because when a gas is produced, it's often produced with another gas. Okay, and the other gas is actually your water vapor. Alright, so in order to analyze the gas correctly, we need to first remove water vapor from the gas. And how do we remove it? Imagine if you have just finished bathing, how do you dry yourself? By wiping with a towel, correct? So your towel acts as a drying agent. So same thing, a gas that contains water vapor, that is damp or moist, we can actually pass it through a drying agent in order to remove the water so that we obtain the dry gas. So in the next part of the video, we're going to look at 3 drying agents that we can use to dry the gases. So these are the 3 drying agents. We can either use concentrated sulfuric acid, quicklime, which is calcium oxide, or fused calcium chloride. Now that we have learned what drying agents are available, we need to find out next which one to use. And to know which one to use, we need to know the nature of each drying agent. So what do I mean by nature? Concentrated sulfuric acid is an acid, so it is acidic in nature. Okay, quicklime, calcium oxide, is actually basic. It's the opposite of acidic, or we call alkaline in nature. Okay, and fused calcium chloride is actually neutral. Okay, so knowing the nature of each drying agent can help us know which gases it can be used to dry. Okay, so let's imagine this scenario again. So there's this boy in the class who got drenched in the rain. Alright, so I need the boy to become dry, if not he will catch a cold. So I need the help of someone in the class to help this boy to dry himself. So who do I want to ask? Do I want to ask the boy sitting beside him or the girl sitting beside him? Alright, so if you imagine the scenario, as a teacher, I would get the boy beside him to help to dry. Why? Is because when I get the boy to dry, I know that drying is the only thing that will happen. Okay, but if I were to get the girl beside him to dry, alright, they have opposite nature, boy and girl. Alright, so on top of drying, they may fall in love, correct? So we don't want that to happen. So this is the same in science. Alright, if we want to dry a gas, we only want the drying agent to remove water. We don't want any reaction. Okay, so we need to get a drying agent of the same nature. So corn sulfuric acid, being acidic in nature, is ideal to dry acidic gases. Okay, quicklime is ideal to dry basic gases. And then neutral drying agents can be used for neutral gases. Alright, this is the recommendation. Okay, once again, acidic drying agent for acidic gases, basic drying agent for basic gases, neutral drying agents for neutral gases. So again, the natural question is, how do I know whether a gas is acidic, basic, or neutral? And for that, the easiest way is again to memorize. Okay, so I've given you the list of gases over here. Hydrogen, oxygen, they are neutral. So the drying agent that I would recommend is your fused calcium chloride. Okay, carbon dioxide is acidic. Chlorine, hydrogen chloride, even though they are neutral, but when you dissolve them in water, when they are put into water, they form acidic solutions. So we consider them to be acidic as well. So together with sulfur dioxide, which is also acidic, the next 4 gases should be dried using your acidic drying agent, which is concentrated sulfuric acid. And lastly, the only alkaline gas in the syllabus, which is ammonia, we recommend using the basic drying agent, which is your calcium oxide or your quicklime. Okay, so before I say something controversial, before I say something slightly confusing, just want to reiterate this. We would recommend, the rule of thumb is this: acidic drying agent for acidic gases, basic drying agents for basic gases, neutral drying agents for neutral gases. Okay, so the slightly confusing thing that I'm going to say is this: actually whatever that I've just said is just a recommendation. The bottom line is this: you can use any drying agent as long as the drying agent does not react with the gas that you are drying. Now for example, hydrogen is a neutral gas, so can I use concentrated sulfuric acid to dry it? The question to ask is, will hydrogen react with concentrated sulfuric acid? Answer is no, because hydrogen is neutral. So in fact, we can also use concentrated sulfuric acid to dry hydrogen gas. So the question that you might ask is this: why can't we use fused calcium chloride to dry all the gases? Since fused calcium chloride is neutral, it is not going to react with any gas. Okay, and that is not true, because even though fused calcium chloride is neutral, it can still react with some other gases. In fact, it can react with ammonia. Okay, it is not an acid alkaline type of reaction, it's some other type of reaction. There are many types of reactions in chemistry, and acid reacting with an alkali is not the only type of reaction. Okay, so that is why we recommend that you remember the rule of thumb that was taught prior to this, but just bear in mind that the bottom line is that the drying agent should not react with the gas that you are drying. Now that we have looked at what drying agents are there and which one to use, the last thing that we'll look at is how do we use each one of them. So we'll start with concentrated sulfuric acid. To use concentrated sulfuric acid, we need an experimental setup as shown. Okay, so we're going to pass the moist gas through the delivery tube into the drying agent, which is concentrated sulfuric acid. Okay, therefore the setup of the delivery tubes are very, very important. The one where the moist gas enters the chamber has to be immersed into the drying agent. Okay, otherwise the gas will not pass through the drying agent. Alright, and the delivery tube that carries the gas out of the chamber need not be immersed. Okay, so the orientation of the delivery tubes is important in the setup for the use of concentrated sulfuric acid. Next, for calcium oxide or quicklime, is a pretty simple setup. All you need to do is to pass the moist gas through a chamber that contains your quicklime, right? And after that, the gas that comes out is your dry gas. And lastly, for fused calcium chloride, commonly we use a U-tube that looks like this. Alright, and then we pass the moist gas through your fused calcium chloride, which is contained in the U-tube. Alright, and the gas that comes up of it will be your dry gas. Now, a common question that you will get related to this concept is this: that you have to draw a setup for collecting a dry sample of hydrogen gas. Okay, there are two key words or phrases in this question. One is dry, so meaning you need to pass the gas through a drying agent first, and secondly is hydrogen gas, so you need to think about how do we collect hydrogen gas. Alright, so at this point in time, what I would suggest is that you pause the video and attempt the question before I go through it in a while. So I hope you have had a chance to try the question. Don't worry if you get it wrong. In fact, many of you will get it wrong. Reason being, there's a trick behind this question. Okay, so first thing, we need to dry hydrogen gas. So what drying agent do we use? We need to go back to the table, and hydrogen gas is a neutral gas, so we'll recommend a neutral drying agent, which is your fused calcium chloride. Okay, so you have to pass your gas into the U tube containing your fused calcium chloride. Okay, this is to dry your moist hydrogen gas. For this part, I believe most of y'all will be able to get it. The tricky part is next part. Now, after drying hydrogen, we need to collect hydrogen. So many of y'all, if you refer to the table that was shown in the video, you might recall that hydrogen is insoluble, and since it's insoluble, all right, many of y'all would suggest using the displacement of water or downward displacement of water method. Now, this is not correct. Why? Because if you were to pass the gas, if you were to collect the gas using displacement of water, you will be passing the dry gas into water again. Alright, so that's equivalent to you drying yourself after a shower and then going into the shower again. So will you be dry? Answer is no. Alright, so in this case it's very tricky because we want dry gas, so we cannot use displacement of water. What other method can we use? We have to use either downward or upward delivery. Hydrogen gas, if you compute the molecular mass, is less dense than air, so the recommended method for collection would then be upward delivery. Okay, so this is the setup for collecting a dry sample of hydrogen gas. We combine the fused calcium chloride with upward delivery, the two experimental setups.